In this video we'll talk about functions. So you've probably came across functions previously in your studies, but you never thought about what the definition is. So that's what we're going to cover today. So by formal definition, a function is a well-defined rule. Well-defined simply means there are no exceptions to the rule. Assigning each x within a set x, the set x we refer to as the domain, to one y within a set y. The set y we call a codomain. The common notation is f such that x maps onto y, defined by f of x equals, and we state our rule. So for example, f of x equals x squared, or f of x equals 2x squared plus 3x plus 1. So the easiest way to represent this is by a diagram such as this. So every single point within the set x has been mapped to exactly one point in the set y. So this one maps into this one maps onto that, this one maps onto this one, and this one maps onto that one. Say we had another point, let's say this point, and this one didn't have a match, then by definition this is no longer a function. Also, if let's say this point went to that same point and it went to this point as well. Now, because it's not assigning each x within the set x to 1 y and y, it's assigning it to 2, then by definition it's no longer a function either. One other thing we have to talk about is the image of f. The image is all the actual values of f of x that we use. So for example, if we use f of x equals x squared, the graph, as we can tell, it doesn't go below the below the x axis. So although our codomain might be the real numbers, the actual image would only be the positive reals. And if you want the formal definition of it, the image of f is equal to the set of y such that y is equal to f of x. The next thing we'll talk about is the different types of functions. There are injective functions, surjective and bijective functions. So we'll start off with injective. So an injective function, every element of the codomain is mapped by at most one element of the domain. And a formal definition, for all x1 and x2 within the set x, so for two distinct x values, such that x1 is not equal to x2, so they're distinct, the function of x1 is not equal to function of x2. So if we look at this on a graph, let's say this value maps onto that one, this value maps onto this one, this value maps onto that one, and this value maps onto this one. No element in the codomain has more than one x attached to it. That's what an injective function is. They can have 0, there can be some that don't have one, but there can't be any that have more than one. So if we imagine, let's say we had another point, and that one went to this point as well, then this function is no longer injective. A good example of this is the function f of x equals x squared. This is because if you think about x equals minus 2, that's equal to 4, and x equals 2, that's equal to 4 as well. There are two different values within the domain which map onto one value of the codomain. And so a good example of a injective function will be any straight line, really, because no matter what number you have on a straight line in the codomain, there will only be one value that maps onto it. So if we have f of x equals 2x, if we pick any real number, say 8, the only way to make 8 out of this function is by having x equals 4. There's no two distinct answers in terms of x. So this covers the injective functions. Now the next one is a surjective function. A surjective function is a function where every element of the codomain is mapped by at least one element of the domain. So by formal definition, for all y, which are elements of the set y, there exists x within a set x such that y equals f of x. And what this basically means is not a single element within y is missed out. So let's say we had this point mapped onto this one mapped onto this one mapped onto this one, and this one mapped onto this one. No elements in the set y have no match within a function x, within a domain x. So if let's say we had another point here and it had no match from any of the x's, then that's no longer a surjective function. A good example of this would be a function which has any break in it. So for example, y equals 1 over x, or f of x equals 1 over x. Because then if we think about it graphically, or well, we don't need to. If we think about what happens at y equals 0, there's no x value to define it. So that's a good counterexample. However, for any good example of a surjective function, we could take f of x equals x squared, every y value within the... Oh, sorry, I meant f of x equals x cubed, because then every single value of y is covered. If you look at it graphically, there's no y value that will be missed out. So that covers surjective functions. Now if you look at bijective functions, all that really means is that they're both surjective and injective. So what that really means by definition is that every y has exactly one x. So in this case, every single y has exactly one x attached to it. Every straight line is a bijective, and there's not really many examples of it. It's just straight lines really. But bijective functions play an important role, because then we need to look at stuff like inverses and composite functions. Sorry, that was supposed to be in a different order. So we'll do inverse first. And for there to be a valid inverse, a function must be a bijective function. Otherwise, we can't find an inverse. So if you look at this example question, y, which is a function of x, is equal to 3x plus 5 over 2x minus 10. We can factorize this, and we get 1/2 3x plus 5 over x minus 5. And so then we can look and say 3x plus 5 is the same as 3x plus 5, and that's plus 15 minus 15. That's all over x minus 5, and that's all multiplied by 1/2. These are equivalent. So then we can rearrange this to have half of, we put 3x minus 15 together over x minus 5 plus 5 plus 15, which is 20, over x minus 5. Now we can simplify this, because 3x minus 15 over x minus 5 is just 3. So it's half of 3 plus 20 over x minus 5. Now from this we can factorize the 3 out, so we get 3 over 2, 1 plus 20 over 3 all over x minus 5. Now, the way we've written this, we can tell that if x is equal to 5, over here you'll be dividing by 0, so x cannot equal to 5. Likewise, the function itself tends to 3 over 2, but it doesn't quite go to 3 over 2 in terms of y, so we can deduce that the function goes from minus infinity to 5, and then from 5 to positive infinity. That's the domain of it. And then it goes to a set which is minus infinity to 3 over 2, and then that's unified with 3 over 2 to infinity. Now, to actually find the inverse of a function, what we need to do is look at the original equation. So we look at y equals 3x plus 5 over 2x minus 10, and we rearrange it in such a way that we get x on its own. So we start off by doing y times by 2x minus 10 is equal to 3x plus 5. Then we get 2xy minus 10y is equal to 3x plus 5. Now we get all the x's to one side, which gives us 2xy minus 3x is equal to 5 minus 10y. Factorizing out the x's, we get x is equal to 5 minus 10y all over 2y minus 3. So that's our inverse function. If we do the same steps to find its domain and codomain, we will find that the inverse function f inverse of y is equal to 5 minus 10y over 2y minus 3, which is in fact equal to 5 times by 1 minus 2y over 2y minus 3. Now if we go by the same directions that we did in the first example, we can tell that y can never equal to 3 over 2, so the domain is going to be everything except 3 over 2, which is the union of these two sets, and it maps onto, the function tends to 5 but it never quite crosses it, so it maps onto minus infinity 5 union 5 infinity. So if we look at the original, we can tell that the domain of the inverse is the codomain of the normal function, and a codomain of the inverse is the domain of the normal function, which is a common knowledge that you'll acquire throughout your studies. One last thing to cover is the composite functions, and there's not too much to do with composite functions. So a composite function, let's say in this case g composite f of x, is exactly the same as you putting f of x into g. So every time you see x in g, you put f of x instead. So in this case, it will be 2 times by f of x is x cubed plus 1. If we were to do it the opposite way around, so f composite with g of x, that's the same as putting g of x into f. And that's the same as doing 2x plus 1 cubed. And that's it for functions. So I hope you understood it. If you have any questions, just feel free to ask. We've got our system done.